Today's video is about dB representation of signals. So dB means decibels, which are a relative unit, meaning that they always express the ratio of two quantities. An important thing to know about decibels is that they are always talking about power. So the definition of how do you express a power ratio in dB is you do this. Whatever your result value is going to be, R is equal to 10 log base 10 of your ratio of two powers. That's the definition. But if you would like to express the ratio of, let's say, two voltages, we'll name that one, the earlier one, RP, and we'll name this one RV. We're not going to use 10, we're going to use 20 log base 10 of V2 over V1. So even though we did this evaluation on the ratio of the two voltages, the thing that RV is actually telling us is the ratio of the two powers in dB. And that's because dB are always talking about powers. You should use a multiplier of 10 in your dB definition for any power or energy type quantity. And you should use a multiplier of 20 for any field, like current or voltage quantity. And obviously, when you are doing this ratio inside the argument of the dB operation, they should always be the same type of quantity. Don't try to take a ratio of a voltage to a current and then convert it to dB. That's not dB, that's impedance. So don't do that. The reason for this difference in the leading multiplier is because the ratio of these two powers, if we're referring to the same system, is always proportional to the square of the ratio of the voltages. Like that. And that's because power is V squared over R, or if you're in phasor domain, it's 1/2 V squared over R. Same thing for currents. Because of this factor of 2 exponent up there, you end up with a factor of 2 multiplied by your dB values. So, what are dB good for? One of the things that dB are really good for, you can actually, I said that they're relative units, but one of the ways that we use them is representing them, representing quantities relative to a fixed value. So if you want to have your quantity, whatever it is, and you want to express it relative to 1 watt, if you do all the stuff to convert that to dB, 10 log base 10 like that, now your quantity is in dBW. The W here obviously is for watts. You can do the same thing with your quantity over 1 milliwatt. You do that, 10 log base 10 of that, you get dBm, where the little m here is for milliwatts. You can do that for dBV or dBA for volts and amps. Now these are both field quantities as opposed to power quantities. So that means that you have a factor of 20 on the front instead of a factor of 10. So to do this, to express something in dBV, you would do 20 log base 10 of your quantity divided by 1 volt. And then you'd get something that's in dBV. dB are really useful because they have all the properties of logarithms. Meaning that log of x times y, for instance, is log of x plus log of y. So the log of a product turns into the sum of the individual logs. The log of x divided by y, which you might be able to guess from this expression, is going to be log of x minus log of y. So the log of a quotient turns into the difference of the two logs. And finally, log of x to the y gets you y times log of x. So exponents in the argument of a log turn into multiplicative factors once you evaluate it. All of these things are really handy because, especially in antenna engineering, we're talking about the differences between extremely large signals and extremely small signals. We're going to talk about antennas that transmit megawatts and antennas that receive microwatts, and that's normal. So in order to express those differences of scale, in order to talk about quantities that vary by orders of magnitude, expressing things in dB is really useful. So that's why we do that. The last thing I want to tell you about dB for today is that there are several common values of dB quantities that you really ought to just be familiar with. Like, it'll be good for you if you know them. The first and most important is if you increase your power by a factor of 2, that is plus 3 dB. So you have added 3 dB if you're expressing that power quantity in dB, and you doubled it. Based on that, you might be able to guess that if you divide your power by a factor of 2, that's minus 3 dB. If you multiply your power by a factor of 10, that's plus 10 dB. And because of the exponent property of the log, if you multiply your power by a factor of 100, that's plus 20 dB. If you multiply your power by a factor of 1,000, that's plus 30 dB. And so on with the powers of 10. There's another one that doesn't come up quite as often, but is still sometimes useful, and that is if you multiply your power by a factor of 3, that's about plus 5 dB. Based on all of this stuff, I can often look at a quantity and guess, within 1 or 2 dB what it actually is. I can write down its value in dB without actually doing the math, because if it's like 20, I know that that is actually 13 dB. That kind of thing you will get used to doing, and it'll help you when you're looking at dB graphs, because dB get used a lot when we're talking about graphs. An important thing to know is that when you are looking at a graph in dB, a lot of the time we'll graph something like the reflection coefficient or S parameters, or something like that in dB. So we'll usually have 0 up here if it's a passive device. And then maybe we'll have like minus 10 dB and minus 20 dB, like that. And 3 dB would be about here. It's weird to look at these things. So you might have a graph that kind of looks like this. And you might be comparing it to a graph that kind of looks like this. The interesting thing about this is this difference on a linear scale is probably much smaller than this difference, because this difference is a factor of 2. Well, this difference is the difference between some value that's less than 0.1, some value that's less than 0.1 and some value that's less than 0.01. Now, on the other hand, if you need a really good impedance match and you're trying to figure out what the operating bandwidth is of this device, this difference might be important. And usually this device doesn't work over here, whether it's 0 dB or whether it's minus 3 dB. You really care about the difference between minus 13 and minus, let's say, 23. But when you're looking at these graphs, sometimes it is important to know that a difference of 10 dB where the top value is already minus 13 is a lot less important than a difference of 10 dB when the top value is 0. Right? So 0 dB minus 10 dB is more important than minus 10 dB minus 10 dB. Which is kind of weird because we're used to a linear scale where those two differences would be equivalent. But in this case, a lot of the time, they're not, and it's important to consider the context. We can talk more about this as we go through the class because we're going to be comparing a lot of different quantities in dB, and some of them are going to be more important than others.